So hello all, this is the last podcast regarding this segment intersection algorithm, which is chapter 2 of our book of computational geometry. I'm going to talk about my implementation of this algorithm that is not totally optimum, but that contains all the ingredients that are required for creating something that will be perfect with small modifications. At first, we need to define data structures for storing the data that are involved in this problem. First, and if we look at the code, which is essentially here, okay, we need a data structure which represents a point. So as you know, all events that occur in this sweep line algorithm are point events. They could be upper points, lower points, intersection points, but they are all points. And one important thing that we talked about, we should be able to sort the points with respect to their y-coordinates. Another requirement of this algorithm is that we should be able to remove and add events on the fly, because anytime we go to an event, we should be able to remove it after it's been treated. And anytime we create a new intersection, it requires to insert this new event inside a container. So, first thing that is required for a point is to be able to be compared with another point. So here these functions allow you to compare two points with respect to its y coordinate. And when 2 points have the same y coordinates, we actually decide to be able still to compare them, but with respect now to its x coordinate. So this kind of ordering is called lexicographic. We take the points from top to bottom with respect to their y coordinates, and if 2 points have the same y coordinate, then we compare them, we store them from left to right. Okay? So this is a unique way of comparing 2 points, and this allows to use data structures that are stored in memory. So for that, I'm going to move a little bit to the other scene, which is my rally camera. Okay, where am I? It's there. Okay, so when you have a point, P1, we can compare it with another point that I call P2. These two objects are said to be comparable. And so I've done it in the code. So this operator has been overloaded. When it's the case, I can store points into data structure that are stored in memory. And those are called binary trees. Imagine you have a certain number of points like that. Okay. P1, P2, P3, P4, P5, and P6. A binary tree actually stores the points in that way. Imagine we start by inserting P1. P1 now is the root of the binary tree. Then we store P2. P2 is above P1. Okay? Imagine that we say that here is under. So left is under and right is above. And under means, okay, less than, and above is greater than. So P2 is above P1, is greater than P1. So P2 is going to be there. Then we're going to insert P3. Okay, we start by P1. P3 is, okay, above P1, but below P2. And we can continue. P4 is below P1. Okay. P5 is below P1, okay, yeah, but is below P4. And then P6 is below P1, but above P4. So it's P5. Okay? So that's the store, that's how pretty much a binary tree works. So whenever you want to find, for example, the guy which is the highest, you take the root here, and you go above and above if there is. So it's P2 here, which is the highest, as we see. So looking at the highest element in a tree doesn't cost you more than the number of levels of the tree. And when this tree is balanced, it means that at any node of the tree, there is pretty much the same amount of load on its left and on its right. It's possible to do that. Then the number of maximum number of stages of the tree, okay, of the levels of the tree, is logarithm in base 2 of n, which n is the number of elements in the tree. It's the power that you have to put to 2 to have the total number n of elements in the tree. So it's so extremely cheap to find the guy which is above. Same thing, it's easy to remove an element from the tree, same number of operation, or add an element in this kind of tree. So trees are going to be very, very well suited to store our events. Events will always be stored in memory. It will be easy to get the one which is above, and it will be easy to add a new event or remove an event. Everything like that will be not easy, but cheap. So of course, it's the right choice for data structure, but implementation. A simple implementation like that, which is not balanced, is quite easy. A balanced implementation is a little more complicated. A very efficient implementation is quite complicated. So what we use implementation that are available. In C++, you have something called the standard template library. For me, that's the only reason I don't use C, but C++ is to have access to this great set of containers and algorithms. And so there is an implementation of this balanced binary tree, which is called essentially the STD set. So if I have a STD set of points, okay, it will store me all the required points with respect to their y coordinate, easy access to the lowest one, to the highest one, easy access to the lowest one, easy way to remove or add. So first thing is a good choice for those points and their containers. So let's go back to the code. Okay, so this is one thing which is very interesting. Okay, next thing is, of course, where do we store the points? All the points. So what I do is I'm storing all the points in one single static vector that contains all the points, which is a static member of points. It's accessible everywhere. Okay, there is a unique instance of that. And anytime I create a new point, I give it an index. The index is the position of the point inside this long vector. You will see it allows easy implementation, easy access to all the points everywhere. Now that I have a point, I'm going to extend that data structure to a thing which is way more specific to the algorithm, which is called an event. An event is essentially a point, as we said. An event is a point. So I store the index of the point, which consists of the event, and then I store its type, because we have three types of events in this algorithm. It's lower, it could be a lower, even the point could be the lower point of a line, the upper point of a line, or the intersection between two lines. So an event has also a constructor, and I give in fact, in this constructor, what do I need? The point, the type, and possibly the two lines that are associated to this event. So if it's an event of type 1 or 2, there's only one line. If it's an intersection, it has two lines. So I store the two lines, so there's a little bit of overhead here. It's not really important, okay? The second line is assigned to 0 by default, okay? And so, like here, it's really the event that is going to be in the binary tree. So I also have a comparison between two events, which actually compare the points. So this is the syntax that allows you to go into the point data structure. This allows to access those semicolons, allows to access this static data, and I go to the pth, it's a pth point, and I compare these two points. So this is really efficient thing. This is a very efficient way of doing this stuff. Okay. So we have got points, we got events. I have a last data structure, which is a line, again, is defined through its endpoints, P1 and P2. And again, I store all the lines inside one single vector that contains all the lines. That's my kind of implementation. If you have another taste, you can do something different. Okay? But any line must store all its intersections. And when it has an intersection, it also stores with what other line it intersects. So every line will have, at the end of the algorithm, a knowledge of all the intersection it has had with all other lines. And again, I store this intersection and all the lines with the intersection are indices of points and other line are indices of lines, which are inside this global container. These are all data structures that are needed to do this algorithm. And now let's go to the code. And let's go to let's go to the main program. So the main program, it's a C main program. You've been doing C at some point of your courses, so you know that in a C program, the input of the main is the entrance of the code, is the main function. It's called at first, and it has always the same arguments. It has a certain number of arguments, and it has a list of strings, which are the arguments. So I first create here a std set of events. So this creates the whole data structure, the binary tree, with all the events, okay, that are stored with respect to their y coordinates. This is debug, and we'll show things like that. So I take the second argument of the argument list of the program will be the number of lines I want to consider. I create the lines. So here I create lines with length are a 20th of the size of the window. If you create very long lines, you may have a lot of intersection as described previously. So I create smaller lines to have a decent number of intersections. I create here a point, a second point, and a line. Here, creating the point not only creates a point, but assign it an index and also put it in the global container. And then I create events, because this is very important. The two events which are important are either the point P1, okay, is above P2, which means that P1 is P1 is below P2. P2 is the upper vertex, and P1 is the lower vertex, or in the other way, it's P1, which is the upper vertex, and P2, which is the lower vertex. Okay, so we've got all our events, and then we have a second data structure here, which contains the status. So this is a simple list. Let's go back to here. So here we have as std the list of, let's say, integers. I mean, I put integers, this size underscore t, it's just unsigned integers. It's a list of integers. Those integers just means the indices of lines. Okay, so it's a doubly linked list. So it means that if we have our sweep line, which is there, okay, and if this is Si, Sj, Sk, and Sl, okay, my data structure will be like that: Si with a doubly linked list. Oh, you could write it the other way around if you want. Okay, so Si points to Sj, okay, which points to Sk, which points to Sl. Imagine now that our sweep line goes to this intersection. Okay, this intersection. What will we do? We will swap Si and Sk. Okay, so when we will just go to the sweep line, go find that we have to swap Sj and Sk, okay, because this intersection point knows about its two neighbors. So we go there, and we can simply, inside it, okay, just change the value here of Sj and Sk. But when we are there, the good thing is that we can now check intersection between intersection here and check intersection here. So it's local. Okay, this guy knows his previous friend in the list, and this guy knows his next friend in the list. The only thing which is not very efficient in my algorithm is that for finding Sj inside that, I do a linear search. This could be enhanced, I know, but it's like that. Okay, I could do it better. It took me 3 hours yesterday to make all things good, so please forgive me for not being perfect here. So let's go back to the code. So how is the program written? I'm not going into full details. I'm just going to give you the basic loop, the basic while loop that actually does all the things that are necessary. So we do this thing. We say while the queue is not empty, this is not while the queue is not empty, we get the event which is at the top of the queue, which is the beginning of the queue if you want. Okay, this is an event. And we erase this event. This is obvious. We said we have to erase the event. Then we compute the position of the sweep line. This is very important because we will have to check all those things in the sweep lines that are on the left and on the right of the sweep line. So it changes anytime we move the sweep line. If it's a lower point, and here I'm going to do the whole explanation when it's a lower point. This is the bad part of my algorithm. As said, I iterate on every line of the sweep line of the status. So it's not a log n search, it's an n search. It's bad. And what I do, if I look if the line of the sweep line corresponds to the line which is the lower point, which this event corresponds to be the lower point. And so remember, I stored those things. Okay, I stored in every event 2 lines. Okay, but here I only need the first one because the second one has no meaning. It has a meaning only if it's an intersection. And so what I look, I look here, this is the current iterator. This is the current iterator. It means it's a current position in my list. And I take the next one. Plus plus means go just on the right. If the right is not the end of the list, so I'm not completely on the right, then I do another thing. I look before. And if the before is not the beginning of the list, so it's not the beginning of the list, then I check the intersection of those two lines. Remember, that's exactly what I told you to do. What this thing does, what this thing does, it goes there, We will have to remove that thing from the list because it's an empty thing. So what I'm doing is that I take the previous one and the next one, those two ones, and I check an intersection. That's the next, and that's the previous. And I check next and previous. Then I will remove it from the list, but the STD list will automatically link those two guys together. So this is the code. I check the intersection. The only thing I will look in the code is this check intersection stuff. So at the end, I erase, ITS from the status. This is the last thing. So what this does, remove it from the list and connect the left one and the right one together to empty the gap that is left by erasing ITS. So you see, I've used this data structure in a very easy way. So I'm not going to go to that. I can give you the code, you can read the code, but it's if the event is an upper point, what do? I add this line to the status, I look in the left and the right of this newly inserted line to check intersection, and if intersection exists, I add those intersections into the queue. If now it's an intersection, I swap the two lines, and I looked on the left and on the right to the newly positioned lines if there is an intersection. So here you see I have the two lines here that are connected to this event, and that's all. That's all for this thing. So, for example, here what I can do is compile. So for compiling, I use G++. On my there. It's there. It's there. That's not easy. Yeah, it's there. You see this yellow window. So G++. I call this thing chap2 as chapter2.cpp. -o chap2, it means that the executable is going to be called chap2. -03 means I want some optimization because standard template library likes to be optimized. And so let's try now. It compiles, it's done. So now let's try to intersect 10,000 lines. I push done. See, the algorithm is not that bad. It has intersected all the 10,000 lines together. Now let's look at the results. So for the results, I have this thing. Yes. So this is the result. So first, let's do a thing like that. Let's do something like that. And let's do a thing like that. So those are the lines. So if you look here, the algorithm has not missed one single intersection. You see here, no intersection here. It has computed all intersections. So these are all the lines. It's a big soup of line. And so I use Gmesh as my code that I will present you at some point for doing visualization. So here, the color of the point is just their index. So if you just see the sweep line. So the lower indices are on the top, the higher indices are on the bottom, and then you see the newly inserted intersection are just from top to bottom, as it is predicted by the algorithm. So you see we have got a result. We can look at the results. Last thing I want to show you is just this check intersection stuff. Let's go back to this thing. Okay, so is check intersection. So checking intersection between two lines is something not very complicated. Huh? So if you think about it, okay, checking an intersection with two lines is quite easy. You have first, let me imagine you have a line, it's x1 and you have x2, okay, and you have here x3 and x4, okay, this is L1 and this is L2, okay, L1 as for equation x equals x1 plus a certain parameter I would call u minus x2 minus x1, okay, L2 is x equals x3 plus another parameter v x4 minus x3, okay, and of course the segments are such that u and v are between 0 and 1. So what you do is you say that the two x's are the same. So you say that x1 plus u x2 minus x1, okay, is equal to x3 plus v x4 minus x3, okay. So essentially you have a system. Those are two equations because it's a vector equation, okay, two equations because there is an x and a y, and those are vectors with two unknowns. So you find u and v, solution of that, and then, okay, if u and v are between 0 and 1, then you have an intersection. So it's quite easy to compute intersection between two lines. It seems easy, but we'll see in a very near future that it's not easy at all. It's easy when points are said to be in a general position. It means that points are randomly put in the plane. If points are not randomly put in the plane, you will have lots of troubles with things which would be like that. So this solution, of course, it's a two equation with dual involves to compute a determinant. And this determinant essentially, okay, is computing pretty much the ratio between the area of this very small triangle and this very big one. And so the determinant could go very closely to 0. And if the point here is very close, for example, to that line, the solution of that is not robust. It means that the point could really be on above that thing, which means there's no intersection, but this determinant would give the wrong answer. So in the future, we'll see how to have robust predicates, which means a robust way of computing such simple geometrical predicates, which means this predicate is a function that actually has a yes and no answer. And here there's two segments of line, yes or no, these two segments intersect. So we'll talk about that. But for intersection, it's pretty easy. So let's go back to the code. And so check intersection actually is very unsmart. It actually computes this determinant, okay, which is there, okay, and computes, if the determinant is very small, I say should use robust predicates, but it does not happen in our case just because we put the points in a random fashion, and here we compute u and v, and we say if u and v are below 0 and 1, we compute a new intersection, and you see here we create a point which is an intersection. Doing that creates a new point in our list. We say that L1 and L2 have these intersections as in their intersection list, and we say that L1 intersects L2 and L2 intersects L1. And then our event here, we create a new event, which is an intersection. It is an event which is intersection. I say 3 for intersection. It has 2 lines, not 1. I insert it in a queue, and here I keep track of all intersections in my code. This is a global variable just to tell me how much intersection I had. Okay, so I will give you the code that does actually the whole thing, but I hope that this explanation has given you tips and tricks to understand this code and this algorithm. Thank you for your attention. This is the last thing I do for you this week.